Hello, my name is Devin Link, and I did my galvanized data science immersive capstone project on embedded machine learning. About me, I'm a mechanical engineer from Colorado State University. Most recently, I was a pipeline integrity engineer for Sinclair Oil, and before that, a field service engineer for Dresser Rand. My goal in this project was to classify human activity using accelerometer data. I started with a data set from phone accelerometer data where I had X, Y, and Z and alpha, gamma, beta accelerations from the phone's internal accelerometer. Alpha, gamma, beta are just angular accelerations. My data was sampled at 50 hertz, and I have 30 participants doing 6 activities: walking, walking upstairs, walking downstairs, sitting, standing, and lying down. I've looked at this raw data a lot, and you can't really determine much from it. So the main hurdle of this project was featureizing my data. I did this in 2 methods. I did X, Y, and Z and alpha, gamma, beta statistics, where I subset my data and took the mean and standard deviation. The second featureization technique I used is called power spectral density analysis. Power spectral density, or PSD for short, is a tool used by engineers to see what frequencies are in our signal. So here we can see that there's a definite difference between our walking and walking downstairs. And the goal of this is to capture the peaks. So I did that by taking the area under the curve specified by these 3 bands. And these bands were chosen by exploratory data analysis. So here we can see the higher the peak, the greater the area under the curve. So I fit this data to a random forest classifier. I started with my spectral density approach, and you can see it does pretty well for dynamic movements, but not as great for static movements. My statistics method did really well for laying, standing, and sitting, and not quite as well for dynamic movements, but still pretty good. I then combined these 2 methods, and you can see I either did as well as my statistics method, or I actually learned information, for example, in walking downstairs. I then went to deploy this model to a Raspberry Pi. Now the Raspberry Pi is just a single board computer with limited resources, but ran into quite a few problems due to the size of the random forest classifier. So I decided to switch to a logistic regression model. Here's an image of me walking downstairs. I'm at the bottom of my landing, and my my Raspberry Pi is correctly classifying me as walking downstairs. Here's a video of me walking upstairs and it correctly classifying my activity. And here's an image of me walking downstairs and my Raspberry Pi incorrectly classifying me as walking upstairs. So what happened? Well, based off my previous EDA, these peaks really should be lining up. As well, I'm seeing that my accelerometer from my Raspberry Pi is in a different frequency domain. We should see this central peak right in between these 2 bands that I specified. Now, I believe this is caused by my accelerometer that I got from my Raspberry Pi is plus or minus 16G. And, human activity is really right around 1G. So I would be operating really on the low end of my frequency domain for my accelerometer. So for future work, I could get a different accelerometer that's plus or minus 2G. I think that would really help my model. I could also implement a different model using Onyx. Onyx allows us to write machine learning algorithms written in Python and deploy them in languages like C. So in conclusion, embedding devices with machine learning is really difficult. Embedded devices are programmed with a compiled language like C or C++, but most machine learning algorithms are written in Python, an interpreted language. Tools are being developed to overcome this problem, such as Onyx, but they're still in development. And separately, but still really important, this approach can be used for most sensor data. If you have any questions, please feel free to reach out to me, and if you want to see more of my previous work, take a look at my GitHub. Thank you very much for watching this video. Thanks.